All right, so we just talked about how we can determine what order reaction we have and how we can solve for the rate law for it, and it's value k. Now we're really going to get into the weeds of all this stuff. There's only two truly common order reactions, first and second order. When I've taught organic chemistry, we've gone through what we call mechanisms of first and second order reactions. And first order reaction involves just one reactant in the reaction where this collides with other molecules like it. The second order is where you have two different molecules colliding with each other and how they interact differently. And in organic chemistry, they get even more detailed as to the differences, nucleophilic versus electrophilic reactions. But we're not going to get into that. Even when we do organic chemistry here, we're not even going to do that. But what we are going to do is the mathematical aspect. So get your calculators warmed up, and you should notice that you had a couple of graphs on there. You might want to pull those up so they're handy, because I'm going to be referring back to them. So be prepared for that. Like I said, reactions occur when collisions occur. It has to collide. It has to collide at the right point. Just because two things bump into each other doesn't mean a collision occurs. It's got to be able to collide at a certain point where there's going to be a breaking of bonds taking place because of the collision. And because of that, and the fact that there are different places or specific places where the collision has to occur, not everything reacts at the same rate. And so that's why we're going through all these graphs here, is to try to figure out how we can predict how much we'll have over a certain period of time. Okay? So, we've got these first order reactions. And let's take a look at a graph. The first graph that I have on there is a graph of a generic reaction showing how you start with a certain amount of reactants, and as time goes by, it decreases. So let's take a look at that. This is that reaction, that graph right there. You see it starts right on the y-axis. Now, they have here x, but what that x really is some concentration of x. And this is where it is at the first, when you have half of it left. And we'll get back to what that is, but the time it takes for that to go from here to here is called the half-life. But we'll get back to that. That's not important right now. What is important is understanding that this is not a linear relationship. This is what we call a logarithmic relationship. We're going to have an asymptote to this line right here. In theory, no, not actually, but in theory, as time goes on, it's going to get closer and closer and closer to zero until there's just like one molecule left, or two molecules that collide, and there's no molecules left. So it isn't going to be a forever thing at some point, depending on the half-life and how quickly they bump into each other and all that stuff. But it will be much further down the line than what this is showing here. This is nice. This helps us understand that it starts at a certain rate. The fastest rate that it's going to go is right here. Now, you imagine a tangent to the curve at that point. That tangent has a particular slope. And as this goes down, that tangent gets less steep and less steep and less steep. And there's a number of reasons for it. What that is telling us is that the rate at which they are actually colliding and producing a new product is getting less and less and less. And the question is, why is it? Why would it make any difference? Well, the biggest difference is the more product that you create, the more obstacles it's got to get through in order to meet another molecule and collide with that thing. And so when you get down here, they're just clustered all over the place with all kinds of molecules, and you got to fight through and ram into one and create whatever products are going to happen. No, it takes a lot of obstruction before it'll finally get to the real minuscule ones over here. So this is why it's not a linear relationship. That's what's going on there. Now, scientists don't like curves. I mean, mathematically speaking. They prefer straight lines. Now, you remember this whole y equals mx plus b thing. And this is something you're taught probably in Algebra 1, maybe a little bit of geometry, definitely in Algebra 2. Whatever, might even been, middle school when you took algebra, you might learn there. I hope you did. This is extremely important. This is a linear relationship. From linear relationships, we can predict values at certain periods of time. That was not a linear relationship. What we had there was this thing going on. That's not linear. But we got to figure out a way to straighten that out. Now, in this particular case, this is dealing with the concentration of whatever it is we're dealing with, and this is time down here. If we could change one of these so that they are both rising or falling at the same rate, then we can get it in the form of y equals mx plus b. Well, it turns out that, like I said, this shaped curve is called a logarithmic curve. So if you want to straighten it out, you take the logarithm of one of the two values. In this case, we're going to take the logarithm of this. So we take a look at this graph right here. And now this is representative of what we just saw. And when we take the logarithm of this concentration over here, we get this straight line. Now, because of that, we have to understand that what they are telling us in this graph. Now, first of all, because we took the, instead of y being the concentration of A like we had in this curve, the y-axis now the natural log of the concentration of A. You have an ln key in your calculator. If you've not used it before, you're going to be using it a lot. Calculus loves natural logs and not log of power 10, the LOG button. So we're going to be using natural log. So the x-axis here is t. So your y equals mx with b now becomes natural log of a equals m times t, x is t, plus the y-intercept b. Okay, so we got two more pieces of information. Slope, y-intercept. Well, the slope is going downward, so it has to be a negative value. The k is a constant. Well, the constant here is the slope. The slope of the line does not change. It's the same all the way down. The constant here is k. So we have found the value k in a negative form. Okay, so now we're going to use negative k for a slope. So now we got natural log of a equals negative k times t plus the y-intercept. Well, here's the y-intercept right here. The y-intercept is the natural log of the original concentration, or the initial concentration. Remember when we did that rate law and K set of problems last time? Yeah, that's what we're talking about here. This is the initial concentration that you have, so they call it A sub 0. So now they turned it around from y equals mx plus b. So I'll rewrite this so that it's in that form. If I can actually find where I know that, there, let's take a look up right now. And, oh, look, I found it. Okay. So, when this turns into a straight line graph by taking, now this wasn't natural log of a right here, this is just a. This becomes the natural log of a right here. And this stays as t. We don't change the t values, and we get the straight line here. And we said that the slope is negative k. And this point right here is the y-intercept. That's our b. and that equals the natural log of the original concentration of A. So I put a 0 there, or I could have put an I there, which is what I did last time. But mathematically speaking, we tend to go with a 0, not at all, but 0. So when the smoke clears and we put all these variables into y equals mx plus b, we get the natural log of A equals m, or x rather is t, m is negative k, put that together, you get negative kt, plus b, which is the natural log of the initial concentration of A, which we call A sub 0.